All right, so today we're going to be talking about the solubility product constant. In a sense, it's just a KEQ, but it's going to be KEQ applied to what we call slightly soluble salts. That is, salts that you dissolve in water, but they're not very soluble. And well, why does chemical equilibrium apply to this? Well, let's say you have a salt like silver chloride. It's not very soluble because, right, chlorides are soluble unless they're bonded to silver ion or lead ion, right, that kind of thing. So this isn't a very soluble salt. So as soon as you dump the silver chloride, right, into your container here, some of the silver ions are going to dissolve. I mean, you will get a little bit of dissolving here, right? So you're going to a little bit dissolve. So you're going to get some silver ion and you're going to get some chloride ion. But very soon, because this isn't very soluble, you're going to reach the solubility limit. Okay? And you're going to end up with what we call a saturated solution. I got to collect my thoughts. All right, so if we kind of look then at this sort of saturated solution, what's going on? Like if we can blow this up, kind of magnify this, you have your solid silver chloride at the bottom of the beaker, right? Because it's saturated solution, it's saturated when 1 grain sinks to the bottom and doesn't dissolve. But remember, we talked about this way back when we talked about solution chemistry, is what ends up happening is you end up setting up an equilibrium, something called, a solubility equilibrium, where it's not static. I mean, this is going to stop dissolving, right, because it's reached its solubility limit. But what ends up happening is it's a dynamic process. You set up an equilibrium. So that's if one silver chloride decides it's going to dissolve, it can do that, but only as long as a silver ion and a chloride ion come back together to make silver chloride solid, right? We kind of drew this up before, okay? And so what's happening, well, then you look at that and you go, oh, there's an equilibrium. At the saturation point, there is an equilibrium that's developed between the solid ionic compound and the aqueous ions. And if you think about that, this saturation point, this dissolution reaction becomes reversible. And if it's reversible, then you can write a reversible reaction, which we're going to look at here in a sec. All right, I know they are. So how about, okay, so here it is. So at saturation, this dissolution reaction becomes reversible. And you can write it like this. Silver chloride solid is in equilibrium with its aqueous ion, silver ion and chloride ion. That's what's happening. That is the chemical reaction, or the dissolution reaction for that picture that we have above. Now, how would it be different if it were a different salt? Well, let's look at calcium fluoride. How would I write what calcium fluoride would look like at saturation? Well, calcium fluoride solid is going to be in equilibrium with O, though. You get 1 calcium ion, but you're going to get 2 fluoride ions, aqueous, okay? And those guys are going to be in equilibrium. If one additional calcium fluoride dissolves, then 1 calcium and 2 fluoride ions must recombine to make the original solid. Okay? All right. Okay. Well, guess what? Because this is an equilibrium reaction, you can write an equilibrium expression. KEQ equals, well, what would it be? Well, aqueous, right? The aqueous product, the silver ion concentration times the chloride ion concentration over, oh, wait a minute. The reactant side is a pure solid, so it's a 1. Okay? And this is why they call it the solubility product. Product here in this case doesn't mean like the chemical product. It means the mathematical product, like times. Look at what this is saying. They call this the Ksp, and it stands for the equilibrium constant, well, the solubility product constant, because if you think about it, this molarity right here, this molarity here, is the solubility limit for silver ion, isn't it? Right? You're not going to get any more than that. So if you figure out this concentration of silver ion, that's going to be the solubility of it. It's going to be the molarity, and that's the most molarity that can dissolve, yeah? So it is literally the solubility, but the product, the little green dot there, it is the product of the solubilities of the ions, okay? And so that's why it's the SP stands for solubility product again. Product is the mathematical product, not like this kind of product here, okay? And so now we're going to kind of see, how this shakes out in a sample problem, okay? And we're going to do 2 sample problems, then we're done, okay? All right, so here's how these are going to shake out. You're almost always going to be given the Ksp, right? And so it says the Ksp for silver chloride is 1.8 times 10 to the negative 10. What would be the concentration of silver and chloride at equilibrium? Or they might ask you, what is the solubility of silver chloride, or the solubility of silver ion, okay? And that they're asking you for the concentration. Because remember, this is the concentration of a saturated solution, and saturated solution, you've reached the solubility limit, okay? So kind of what Brendan was asking about before. Okay, so here's the first thing. You got to do, when you get a Ksp problem like this, do 2 things. 2 things, right? First, write the balanced equation for the dissolvent. Second, write the Ksp expression that goes with it, the KEQ or Ksp expression. I like to draw a little picture. I love drawing little pictures, right? Calorimeters, heat curves, beakers with slightly soluble salts. But the equation is, and here's why. Because you're going to find out that the mole ratio between these ions is going to be key to the solving of this problem. And if they're staring at you in the face that this is a 1-to-1 mole ratio between silver and chloride ion, that's going to be key to solving the problem. Okay, so then you write the KEQ expression, which you can now call the Ksp expression. And you're going to set it equal to the Ksp value that was given. Okay? And so here, that's my balanced equation. We saw it up above. And here is my Ksp expression. And now, well, how do you find the solubility, or how do you find the concentration of silver ion and chloride at equilibrium, like I asked you before at the top in the prompt? Well, you're going to solve for x and y. Wait a minute. How can you have 2 variables here. How can you solve for 2 variables, 2 unknowns? Well, because they're not 2 unknowns. We know something about x and y. In fact, if x is the concentration of silver and y is the concentration of chloride, don't they have to be equal because of the 1-to-1 mole ratio? So it turns out that x equals y. Your silver ion concentration equals your chloride ion concentration because of the 1-to-1 mole ratio. So then wherever you see chloride ion, you can plug in silver ion. Yes? It's a direct substitution. So here we have, up above we have, x times y equals, 1.8 e minus 10, but x equals y. So here's what we're going to do. So I rewrote it down here. Well, the Ksp, silver times chloride, equals 1.8 e minus 10. Wherever I see chloride ion, I can substitute silver ion. I could actually do it the other way. I could say chloride ion times chloride ion, but I just did it this way. And so basically now you have x squared equals the Ksp. Yeah, it's pretty simple in the final estimation. All right. So the silver ion squared. If anybody had a calculator, I'm going to get the square root here in a second. And so when I take the square root of both sides to get the silver ion concentration, I get 1.3. And there's really only 2 sig figs. Times 10 to the negative 5th. And now you can actually say molar because this is a concentration. Even though it was unitless before, you're solving for a concentration now. So you can put in the molarity. So that would be the solubility of this salt. So what's the chloride ion concentration? It's going to be the same, okay? And because there's a 1-to-1 mole ratio between silver ion and here, then you can say that that is the solubility of AgCl. Like AgCl itself is never going to be more than 1.3 times 10 to the negative fifth molar. Got it? So sample number 2, we're going to look at the dissolution of calcium fluoride that has a Ksp of 1.5 times 10 to the negative 10. All right? There's my equation. Calcium fluoride is in equilibrium with its ions, but in this case, there's a 1-to-2 mole ratio between the ions. And so then the prompt is asking you, what is the solubility limit, the saturated solution concentration, of calcium fluoride given the Ksp has this value? So what did I do? I wrote the balanced equation, and next, what's the next thing I did besides drawing a picture? I wrote the Ksp expression. Do those 2 things, and you should be good. All right, that's your number 1 way to start these. Okay, in fact, even any equilibrium question, if they didn't give you the balanced equation, write the balanced equation, and then write the darn KEQ. I mean, this is like the start of anything equilibrium. Okay, all right, so here it goes. There's my equilibrium expression. And remember, I got to square the fluoride ion, don't I, because of the 2 in the balanced equation. And so now, if I shake it down, and if the concentration of calcium is x and fluoride is y, I got x times y squared. And you're like, oh man, but no. But we know something about the relationship between x and y. And this is where you got to be careful. I know that the fluoride has a 2 in front of it, but what you got to say is to yourself, okay, how can I come up with an equivalence between x and y? Well, if you look at the balanced equation, I always look at the balanced equation, I go, whatever this concentration is going to be 2 times that, isn't it? Because you're going to get twice as many moles in the same volume of fluoride as you are calcium ion, okay? So if you just say that to yourself, I say to myself, the fluoride ion concentration is always going to be twice that of calcium because of the 2. So now we have our equivalence. Y equals 2x. If you're using the x and y notation, right? So that y, that concentration of fluoride, is always going to be twice the concentration of calcium. And so now I can write my Ksp expression in terms of just x's, calcium ions. Okay? Let's do it. All right, so there's my Ksp expression rewritten, and now I want to substitute. So wherever I see fluoride ion, I'm going to put in my equivalence that fluoride ion is 2 times calcium ion. So I'm going to fill this in. I'm going to go through each step. Calcium ion times, and then 2 times the calcium ion concentration squared. So that ends up being 4 calcium ion squared. Yeah, 2 squared, calcium squared. So I get calcium ion, right? I'm going to just do this real quick and dirty. 4 times calcium ion squared, right? You got that. Oh, what's it going to end up? 4, the Ksp equals 4 times the calcium ion concentration, what? Cubed. And that equals the Ksp value of 1.5 times 10 to the negative 10. Solve for calcium ion concentration. So first, calcium ion concentration cubed is going to be this number divided by 4. And then you're going to take the cube root. All right, so we solve for calcium ion cubed. Get this number, 3.75 times 10 to the negative 11. Take the cube root of both sides, and we will get the final answer. All right, you take the cube root of both sides, and you find that the calcium ion concentration is equal to 3.4 with just 2 sig figs. Sorry, 3.3 times 10 to the negative fourth. And here you can say molar. What would the fluoride concentration be? Somebody tell me. 6.6 times 10 to the negative fourth molar. Now, I know we did some rounding, but think about it. If you took this number and you multiplied it by this number squared, you better get 1.5 times 10 to the negative 10th, huh? Right? And that's a way to double check yourself. All right? That's KSP. These are the kind of problems you're going to encounter there, but you might also have questions about what's going on with that equilibrium, involved, and that's going to be on the worksheet. All right?